In this video, we're going to derive the equation for the general solution of a problem of continuum mechanics for small strains and for isotropic linear elasticity. The solution is also known as the Navier's equation. As we know, for any problem of continuum mechanics, we need to solve the equilibrium equations, the kinematic equations, and the constitutive equations. And we have to put all of these together in order to solve one main equation. And that's going to be our objective today. All right, so the plan is going to be to put equation 3 into equation 1. And once we have equation 3 into equation 1 as a function of strains, we'll put equation 2 into those two combined. So let's get started. And the first thing that we're going to do is to write the equilibrium equation, but we're going to reduce this just to the coordinate number 1. We're going to extend later this to the 3 coordinates, but let's just start with coordinate number 1. So in here, actually I have 3 equations for the 3-dimensional space. And the first equation for coordinate number 1 is as it follows. Plus the variation of this shear stress in direction 3 plus the force in direction 1. And this should be equal to 0. Okay, so what we're going to do now is we're going to replace what each of these sigmas are as a function of the strains through the constitutive relation. And in order to do that, we're going to have to use and populate the stiffness matrix. So we're going to use one simplification here, which is going to make our deduction and our derivation a little bit easier, and is that we're going to use the Lamé parameters. So sigma is going to be equal to, as we know in Boyd notation, sigma 1 1, sigma 2 2, sigma 3 3, and sigma 2 3, sigma 1 3, and finally sigma 1 2. And now, instead of writing this matrix as a function of the Young modulus and Poisson ratio, I'm going to write it in terms of the Lamé parameters that we're going to see in a bit what those are. This is lambda, lambda, lambda plus 2 times mu. So the two Lamé parameters are lambda and mu. Remember that for an isotropic linear elastic material, we just need 2 parameters in order to fully define the properties of this solid. All right, so let me complete this vector and the matrix, and we'll continue with the second step. Remember, these are going to be all zeros, and this is going to be symmetric. And here I'm just going to have mu 0 0 mu 0 mu. Okay, what are these Lamé parameters? The Lamé parameters are lambda, and you can verify this with your stiffness matrix that we derived some time ago. And mu is just the ratio of Young modulus divided 2 1 minus Poisson ratio. And if you remember, this is just a shear modulus. So actually the only new parameter that we have is lambda, Lamé parameter, or first Lamé parameter, and the second Lamé parameter is just g. All right, so We're going to use now this matrix in order to write whether sigma 11, sigma 12, and sigma 13. All right, so let's do this. And these equations are going to be a little bit long, so hopefully I'm going to have space for this. First one, sigma 11. Sigma 11, as you can see from the matrix, is going to be lambda plus 2 times the shear modulus times epsilon 11 plus lambda times epsilon 22 plus lambda times epsilon 33 and nothing else, because these are going to be all zeros. That's going to be sigma 11. So what I'm going to do is I'm going to use as a common factor lambda, since it appears in all the strain terms, and I'm going to separate these and put 2 times the shear modulus over here. And remember that this 2 is coming from over here. All right, that's sigma 11. Let's write now sigma 12. Sigma 12 from here is just going to be the product of the shear modulus times 2 times epsilon 12. Let me bring the 2 to the front. So this is going to be 2 mu epsilon 12. And similarly, we're going to have something like that for sigma 13. And finally, we have our body force F1, and all of this is going to be equal to 0. Okay, next step, now that we have the equation written in terms of strain, we're going to write the strains in terms of gradients of displacement. So let's do that. And now this one is going to be a little bit longer. And so far this is the same, but now remember the definition of epsilon 11 is this plus that, and something similar for direction 3. Now for the shear part of sigma 11, we have epsilon 11, and I can close the parentheses, go to the next term, and here this is going to be 2 mu, and now the definition of epsilon 12 is 1/2 of du1 dx2 plus the cross derivative du2 dx1, and something very similar is going to apply for the third term. And this is going to be now with respect to direction 3. Okay, I believe I have almost everything. I just need to add the body force in direction 1, and this is going to be equal to 0. All right, so let's see how we can simplify a little bit this equation. And you can already see that there are some here. Let me use a different color. We can get rid of these two, these two, these two, and that two, and I'm going to write again this equation, but I'm going to reorder some of the terms, so it's going to be easier to recognize those later on. And I'm going to use also some common factors. Okay, let's start with the first term. The first term, I can take lambda out of the derivative because lambda is a material parameter and it is a constant. And let me now open a bracket. and this is going to be the derivative with respect to direction 1 of what I have in between the parentheses, and close the parentheses. I'm gonna also close here the bracket, and I'm missing this term over here. So what I'm going to do is just to write it separately, and this is going to be 2 times mu. Remember, mu is also a constant because it's a material parameter, but we have a derivative over here. So now this is going to be a second derivative of u1 with respect to x1 2 times. And similar to that, what I'm going to do is I'm going to now apply the derivative x2 with respect to these 2 terms. I'm going to bring the parameter mu out of the derivative, and this is going to be the second derivative of u1 with respect to x2 2 times for the first term, and the second term is going to be mu times the derivative with respect to x2 of du2 dx1. And notice that now these are different directions, so I cannot put them together. And a similar thing is going to happen with the third term. Second derivative here, and I can, for the last one, it's going to be mu, and let me save some space here. I can also write this like this. It's the same one to what I have, same thing as what I have over here, and this is going to be plus f1 equal to 0. Okay, we've got quite a bit, quite a long equation right now. What we're going to do now is to try to organize all of that into a simpler version. All right, so let's start from, let's go from left to right. The first part, there is not much else that we can do, but what we're going to do is to recognize what is in between parentheses, and this term between parentheses can be simplified to a shorter notation, which is going to be, let me write it with colors here. All of this is going to be the divergence of the displacement vector. Notice that the null operator is it's a vector, and it's just the derivatives with respect to x1, derivative with respect to x2, derivative with respect to x3, and this is dot product, and it's combined with u1, u2, and u3. So when you add all of these up, you get what you see over here, and written in the vector notation is like this. All right, let's go to the second term. The second term is, I'm going to bring together here one of these terms. I'm going to bring also this term over here and this term over here, and all of these is going to be, let me continue with the same color, it looks good. It's going to be mu d u1 second derivative. Notice that, as I told you, there are two of these terms because it's multiplied by 2. I'm just taking one, okay? And this is u1 x2 and the other one is du1 dx3. I'm making all of these associations in order to make the notation more compact later. Okay, so now that I have that, what is this? What we have in here can be simplified to the Laplacian of displacement 1. Notice that it's second derivatives of displacement in direction 1 with respect to each of these directions, and all of that added up. And remember that we have a shear modulus over there. And let's see what is left. What is left is, I'm going to use also the common factor mu, and this is going to be the derivative with respect to x1. The first thing which is left is one of these. And one of these, in order to make it equal to, with this common factor, to what is left, I'm just have to add here a derivative with respect to u1 x1. And notice that for this term and for that term, I can bring this into what is going to be this term over here, and I'm going to use the property of the cross partial derivatives, so I can write this equation but with this dx1 to go first and the dx2 to go second. So if the dx1 goes first, that's my common factor, the dx2 goes second, this is going to be du2 dx2, and the same thing for the other parameter. And now this is starting to look like something that it's easier to understand. And the only thing I'm missing here is f1, but let me also write what this is going to be. Okay, so I've got that part over there, and again this is going to be the same thing that I have on the left, right? So this one is going to be also the divergence of the displacement vector plus f1 equal to 0. All right, so we're very close to the end. What I'm going to do now is now I can use as a common factor this divergence of the displacement vector, and what I'm going to find out is that if I bring this now, lambda of d dx1 of the divergence of this, and I'm going to bring the third term plus mu dx1 and the divergence of that plus mu the Laplacian of the first displacement plus s1 equal to 0. Now I can have as a common factor this derivative with respect to direction 1 of the divergence of the displacement vector. Okay, so we have been able to compact quite a bit this notation, but remember that this is valid just for coordinate number 1. And what we're going to do is we're going to generalize this for all the coordinates. And as you can see here, for direction number 1, the only ones that appear are here, there, there, and there. So I could have done the same for all the directions and I will get exactly the same equation. What that means is that I want to have three equations like this, but then instead of the one, I want to have 2 and 3. And I could write that, but I won't. I will just write directly the final equation uh, that involves the 3 direction. And this is going to be lambda plus mu, which come from over here, times the gradient of the divergence of the displacement, and this involves these first two terms, plus mu, the Laplacian of the displacement vector now, plus the body force in vectorial notation is going to be equal to 0 vector as well. And this is the final equation, and this is what is known as the Navier's equation for linear elasticity, and in this case for linear isotropic elasticity. Notice that you could do also a solution of the Navier's equation, for example, for an anisotropic solid. The only step that you have to change is to change the stiffness matrix. And probably it's not going to look as compact as the equations that we have right now, but it is going to be your Navier's equation, the one that you're going to have to solve. So what do we have in here? These inverted triangles, as we see, those are derivatives with respect to space. And again, that's the operator nabla. And since they are derivatives, this is just a differential equation. And this is the differential equation that we're going to have to solve in problems of mechanics, where u is going to be our unknown. For those of you more familiar with fluid flow problems, in a problem of fluid flow in a reservoir simulator, for example, our unknown for one phase is pressure. Our unknown in linear elasticity and in this differential equation is displacement. Okay, so we are going to see some solutions for this equation. For some of those, we'll just see the answer for that, and we are also going to see the derivation probably just for a few of those, because it's actually pretty hard. It's the math involved in solving analytically this differential equation. It can get quite complicated. So for the solution then, we're going to have an analytical solution for the equation. For that analytical solution, for example, I could have here, there are different methods in order to do this. You can invoke the Beltrami-Mitchell equations of strain compatibility, and that is going to guarantee certain properties of the cross derivatives and of the strain field. The compatibility, this long word, let me write it first, that is going to help you to solve this problem. Because as we have seen, calculating strains from displacements, it's quite straightforward. However, calculating the displacements from strains, it's not. So that's what the Beltrami-Mitchell equations help you for. And another solution here is to use the Aries functions. With the Aries functions, what you do is you postulate a solution for your equation, and you just check if that works or not. And usually this is done through this type of function. This is an Aries function, where, for example, from here, your stress sigma 1 1 is the second derivative of this Aries function phi with respect to x1 two times. And you can see more about this in the book of Malvern, but we're not going to see these solutions in detail, how to do those. Again, some of them are quite complicated, but what we're going to see are some examples. And those examples are going to be the Kirch solution for computing stresses around wellbores, the Griffith solution for calculating stresses around a linear fracture, and also we're going to see the Snedden solution for calculating stresses, the stress field around the fracture. What we are going to do, and what you're probably going to do later in your life and in your professional life, if you get to work in geomechanics, is to calculate numerical solutions. And for numerical solutions, there are several options in order to solve the Navier's equation, and you could solve this through finite differences. An example of a software that solves the mechanics equation with finite differences is the software called FLAC. Some of you may be familiar with it. Or you could also solve, or you can use the finite element method, also known as by its initials as FEM, and here, for example, you have software like Abacus that looks for solutions of this equation, and what we're going to work with is with a free software which is called FreeFEM++. And if you are interested into also these solutions, there are some other options like Phoenix, or also like Console. All right, but in summary, there are several solutions that or approaches that you can use in order to get to the solution of solving this differential equation. And what we're going to see next is how to use numerical solutions in order to solve this problem. Numerical solutions are particularly well suited to problems in which you have complex boundary conditions. The analytical conditions usually are good for relatively simple boundary conditions. While the numerical approach, it is valid, and it is more efficient for problems that have boundary conditions which are quite complex.